So that's where I'm going to leave you hanging with that video clip. What you saw was Indy adjusting the bag of sand to be about the same size, the same volume as the gold idol. So it shouldn't have triggered the trap, right? We're going to assume that the gold idol and the bag of sand had a volume of about 1 liter. 1 liter is about 1,000 milliliters. Question to you is, how heavy is the idol? How heavy is the sandbag? To answer these questions, we're going to need to use the density equation. The density equation is mass divided by volume, or D is equal to m over v. We can rearrange this equation by cross-multiplying. We can cross-multiply using the PowerPoint pen. Hopefully will work here. It is not working here. Here we go. Density times volume equal to mass. So mass can be, this equation can be rearranged to read mass is equal to the density times the volume. If we want to solve this for volume, we'd have to divide both sides by D. And we could rearrange this equation to say volume is equal to the mass over density. Using the version of this equation solved for mass, mass is equal to density times volume, we can figure out the mass of the gold idol and the mass of the sandbag. The mass of the sandbag is equal to the density of gold, 19.3 grams per milliliter. We're going to multiply it by the assumed volume of the gold idol to be about 1 liter or 1,000 milliliters. If we multiply these two numbers, milliliters will cancel, giving us a mass of 19,300 grams. If we do the same math for the sandbag, the density is 2.65 grams per milliliter. And since Indiana Jones made the bag of sand about equivalent in volume to the gold idol of 1,000 milliliters, we can now see that the mass of the sandbag was only about 2,650 grams. So if the trap was really set to be equal to the equivalent mass of the gold idol, how many sandbags would Indiana have needed to match the mass of the idol? Well, 19,300 grams was the mass of the idol, divided by 2,650 grams of the sand. He really should have had about 7.28 bags of sand on that pedestal to keep the trap from being triggered. This for sure leads us to a conclusion that Indiana Jones is the most dense of the three options, gold, sand, or Indiana Jones. We're going to work through a couple of density equation examples. Here we see a weather balloon is inflated to a volume of 2.2 times 10 to the third liters with 37.4 grams of helium. What is the density of helium in grams per liter? Since we're being asked to find the density of helium, we'll use the original equation already solved for density. Density equals mass over volume. This is a pretty straightforward problem. The mass is already given to us at 37.4 grams. The volume is given to us as 2.2 times 10 to the 3 liters. Make sure when you're dividing by this scientific notation number that you do use parentheses in your calculator. Mathematically, this calculates out to 0.017. The units don't cancel, and that's good. we should have units of grams per liter. So that's the density of the helium sample in the problem. The next problem is, what is the volume in cubic centimeters of a sample of cough syrup that has a mass of 50.0 grams? The density of cough syrup is 0.950 grams per cubic centimeter. Since they're asking us to find the volume, we should use the version of the density equation that's already solved for volume. We earlier decided that volume was equal to mass over density, and now it's a simple, straightforward plug-in problem. 50.0 grams divided by 0.950 grams per cubic centimeter. Grams over grams will cancel, and since we have three significant figures in both our numerator and denominator, we should round our final answer to have three significant figures, and you should get a calculated result of 52.6 cubic centimeters. One final density calculation here. What is the mass in grams of 14.0 liters of gasoline? Assume that the density of gasoline is 0.680 grams per milliliter. Since we're being asked to find the mass of this substance, we'll use the form of the density equation that's already solved for mass. Mass is equal to density times volume. Since we know the density to be 0.680 grams per milliliter, and we know the volume is 14.0 liters. This is almost a straightforward problem, but you might see here that this liters measurement here, this unit of liters, will not cancel with the milliliters in the density number. So we are going to need to make sure that we convert our 14 liters into milliliters. Since there are 1,000 milliliters in 1 liter, each one of those 14 liters has 1,000 milliliters. So we can substitute in 14,000 milliliters. Now the milliliters will cancel. We had three significant figures in our original measurements of 14.0 and 0.680, so our final answer should also be rounded to 3 sig figs. So your calculated answer should round out to 9,520 grams. Make sure that you can verify this in your calculator. Don't just write it down and assume that you can do it. Talking about density of various substances, we're going to take a look at the density of the noble gases. The noble gases are the elements found all the way to the right of the periodic table, and you can see here a list of the densities: helium, neon, argon, krypton, and xenon. Their masses, or their densities, progressively get greater and greater, and that's because as you go down a column in the periodic table, the masses get heavier and heavier. Now, comparing each one of these densities to the density of air, you might be able to make a prediction as to whether or not these gases would float or sink in air. We're going to take a look at a video clip so you can see if your predictions are correct.
Here are 5 of the 6 noble gases: helium, neon, argon, krypton, and xenon. They're all colorless and transparent. Krypton and xenon form compounds only with difficulty. Helium, neon, and argon don't form compounds at all. As we descend the group in the periodic table, the atomic number and the relative atomic mass increases. The gases get denser. Helium is lighter than air. Neon is just lighter. Argon and krypton, I've just got to unstick these from the anchorage for a moment. Argon and krypton are both heavier than air. And xenon is the heaviest of the lot. You've heard of a lead balloon? Well, this is it.
So maybe you could actually even hear the sound of the xenon balloon hitting the ground. It was so dense you could hear it actually hitting the ground. One more video to show you. This video is the reverse of helium. You know what helium does to your voice if you inhale it and let that helium gas come out through your vocal cords. You know that helium makes your voice sound much, much higher. Well, that's because helium has a density much less than air. So what would happen if you were to have a gas that is much heavier than air pass over your vocal cords as you're trying to speak? Well, the video clip I'm going to show you is from the Ellen DeGeneres show, and it's she had on her show a couple years ago a gentleman named Steve Spangler who will demonstrate this for you.
Next guest knows how to make learning fun from Littleton, Colorado. Please welcome science guy Steve Spangler. Nice to meet you.
Nice to meet you.
So, all right, what are we doing?
Okay, so I think the first science experiment anybody ever did was maybe breathing helium. You know what I'm talking? So you breathe helium and your voice goes
I got to
really
tell
high.
you, I never took science class. I swear, I never did.
Okay, so this is your first science
It
class.
is.
So this
It
will be
is.
fine. All right,
Okay.
so you breathe helium and your voice goes really...
Yeah, I've done the balloon thing.
Yeah, okay.
High.
Right.
Yes.
So
And
I was
is that
thinking-
okay to do to your vote? Is it safe? Is it dangerous to?
We always say, don't try this at home.
Okay.
Try it at a friend's home.
Okay.
So if you... So, I mean, that's the legal thing.
Okay.
All right, so helium is 6 times lighter than the air we breathe. So I was thinking, what if we used a gas that was 6 times heavier than the air we breathe?
It'd be different.
Yeah, so here, watch this. So, see, that's already good. You did a good job.
Right.
All right, so here we go. So this, okay, so you're just going to hang on to this. So this gas is 6 times heavier than the air we breathe. And I'll show you.
It's heavy.
Oh, that tricked me for a
Yeah,
second. All right, so here we go. So now, watch what's going to happen. So what I want you to do, I'll teach you how to do it. You're going to breathe all your air out. You're going to go, and then I want you to breathe in about half of the balloon, and then just talk to the audience. Okay, ready? Keep going, keep going, keep going. Okay, now talk to the audience.
All right, I will talk to the audience. Oh, wow.
Isn't that cool?
Yes. Luke, I am your father. Isn't that kind of weird? Yeah, that's very weird. That's so weird.
And it only,
You okay? You okay?
It's lightheaded.
Yeah.
So breathe in. Only problem is that you stay like this for about 3 weeks.
Well, yeah,
all right?
it's still going on in my voice.
I know, it's all right. All right, so breathe in, ready? Now breathe out. See, you're good now. Try it again.
I hope I am. All right.
See, you're good.
I think so.
Okay, you're good. All right.
This is ridiculous. All right.
See, but now this kind of makes science fun. I always tell teachers, if it gets to the dinner table, you win. You know what I mean? So
yes.
kids talking.
And on that note, this concludes the video lecture on density. Thanks for listening.